We can also actually assume that x epsilon j, t epsilon j, and j goes to infinity, converges to x0, t0, which is the strict maxima of u minus 3. Okay. Now good. So far so good. We have u epsilon j minus 3 as the local maximum at this point. Now look back at the PDE. That's why now the philosophy is very important. Now you look back at that. That's why I mentioned viscosity solution is kind of equivalent with maximum principle because we're gonna use maximum principle. Now look back at the PDE. Okay, u epsilon j and phi are smooth, no problem, right? As smooth as you want. Smooth. Okay. At the maximum point, surely we have du epsilon j, x epsilon j, t epsilon j is equals to d3. Right? And then the Laplacian is less than equal, just sort of by maximum principle. Okay, I'm using the fact that, for example, I have a function c that has the maximum at this point, and I have the gradient is equal to 0, and I have the Laplacian is less than equal to 0. I can move the calculus. I'm using this one first. Very simple. Now, if I want to plug back into the PDE, what do I have? Oh, I forgot. I also have u epsilon t. X epsilon j, t epsilon j is equal to 3t, x epsilon j, t epsilon j. So you see, this is kind of L infinity and allow that function because you really see that I also do kick the derivative to the test function. Right? I kick the derivative to the test function in the L infinity. This is a very important very important philosophy. Now I look at the PDE, what do we have? I have 3t x epsilon j, t epsilon j, plus h x epsilon j, d3 x epsilon j, t epsilon j. Now I have the Laplacian is less than equal to the Laplacian, so epsilon. Okay. You see, isn't it amazing, right? I mean, now we have the test function. We kick everything to the test function, right? Now, and then the test function is smooth, it's nice. So I'm gonna let j goes to infinity. This converges to the x0, t0. So this goes for what? This is smooth, nice. Epsilon j goes to 0. So I have 3t x0, t0. Plus h x0, d3 x0, d0, that's equal to 0. So this is an additional information I have from the balancing viscosity procedure. Right? Via test function. I don't do integration, but somehow I still have some inequality. Okay, and similarly, any questions so far? Okay, similarly, if u minus 3 has by the way, the shrink thing is not important, but has a shrink minimum at x0 to 0, and I forgot to say that t0 has to be greater than 0. I don't want it to be at 0, but if u minus 3 has a strict minimum, then I'm going to have Because reverse inequality, if t x0 t0 plus beta x0 in free of x0 t0 greater than equal to 0. So I have the reverse inequality. Okay, so that's sort of two addition of inequalities that I have two more things that hidden, we don't see it in the PDE. But if we were to think about it more and more, we would get something kind of like from there. So that's sort of Craig Evans derivation. And then now we can give a definition. One, let's say U is continuous. Somehow we're going to suppose that it's bounded as well, it doesn't matter. It's a viscosity subsolution. If for any free smooth, C2 is fine. C1 is fine. Sorry. If U minus 3 has a shrink max at x0, t0, let me call this one 1. That 1 holds. So we call it a subsolution. Sub because we have less than sub. And second, if we have U is in C, Rf, non-zero infinity, is a viscosity super solution. If for all 3 in C2, if U minus 3 has a shrink mean at x0, t0, that 2 holds. This is 2. So we assume this to be the definition of viscosity solution. And 3, U in C of Rm times 0 infinity is a viscosity solution. If U is a viscosity sub and a viscosity super solution. Okay. So the name, this is a name that Randall Leon set it to be viscosity solution. It's kind of confusing because from the first derivation we derived it from balancing viscosity method. So that's why Randall strongly wanted to derive it as viscosity solution. But it's sort of misleading because later if we go to second order equation and so on and so forth, the balancing viscosity method doesn't make sense anymore. We need to use Paris method derived by Hitoshi Ishii. And for second order, we need to use the result by Bob and later by AC and so on and so forth. But for historical reasons, they still keep the name by viscosity solution, which is very weird. It's when I translated it to Vietnam, when I first saw it, it's kind of, let me say it in Vietnamese, it's like, which is, doesn't make any sense. Yeah, every time I think of viscosity, it doesn't make any sense. It was something. Anyway, so now let's go back to the example I provided to see what's going on with this definition. Okay. By the way, so Craig Evans gave this definition and so on and so forth, but he told me like at that time he didn't know or he forgot one of the most important questions, which is like, how about uniqueness? You have some selection procedure. How about uniqueness? He didn't give a proof. And then Crandall and Leon in the early 1980s gave a proof of uniqueness, which is the extremely important result. And that's really opened the era of viscosity solutions. Okay. So before doing Crandall Leon's uniqueness proof, I want to look again at the example. Okay. When I studied, I didn't look at it this way, but I think it's better to give you some sense of what's going on. It's always the case. back to the biology example. To the biology questions. Feel free to ask a question. I mean, like, what I'm doing here is not in the historical or everything is messed up, you know, one back. I want to give you some taste. I mean, this is like my personal taste about that, how do I think about that. Okay, look back at this. What does that mean by having such a weird definition of dissociative solution? Now, we all see that any guys of this form is a solution almost everywhere, right? So let's check this one to see if it's a dissociative solution. So let me call this one U, 0, 1. So check. In the yellow guy is a viscosity solution. Why not? Why don't we check? So of course, it doesn't make sense to check here, right? It doesn't make sense to check at the smooth things. Everything is smooth, we don't have to check. The only two things we need to check is the 2 points. 2 points that we have discontinuity of U curve. We need to check at those points. Now let's have a picture proof. Can I touch this one from below? I mean, this is a corner, right? This is a corner. I cannot really touch this function from below. There's no way that I can touch this guy from below or something like that. So by some function. Of course, this is kind of like a heuristic way, but surely I can always put any test function free like this, any test function I like, to touch it from above. What do I mean by touching from above? So let's say this, let me call this one quantum. So F